All right, now we can talk about confidentiality is in wireless communication. So we start with word equivalent privacy WEP. So the standard we're talking about was 802.11. So this standard originally defined WEP to protect the confidentiality of data using RC4 stream cipher encryption. So as you might guess, WEP has an unfortunate name with claiming word equivalent privacy, but unfortunately it is broken. So it has a very unfortunate name. So WEP is an insecure protocol that is easy to crack. We talked a little bit about this when we were talking about RC4 stream cipher. So one of the main problems with RC4 was the non-randomness. So by using this non-random behavior, people introduced many attacks, and those initial attacks were, some of them were as follows. So passive attacks to decrypt traffic based on statistical analysis, active attack to inject new traffic from unauthorized mobile stations based on non-plain text, active attacks to decrypt traffic based on tracking the access point, and dictionary building attack that, after analysis of about a day's worth of traffic, allows real-time automated decryption of all traffic. So these actually somewhat improved, and currently we have better attacks, which I'm going to talk in a minute. So as we mentioned, WEP uses RC4 to encrypt packets for transmission over IEEE wireless LAN. To avoid producing the same key stream, WEP requires each packet to be encrypted with a different RC4 key. And RC4 key used for WEP is a concatenation of a 24-bit IV and a 40 or 104-bit long-term key. So as you might guess, 40-bit security is not enough. You can perform an exhaustive search to a 40-bit attack using just a single laptop. But even if you increase the key length, the IV is also very short. So 20-bit IV is too short. So just using these weaknesses and non-randomness property of RC4, one of the best attacks was due to Fleurer, Mantin, and Shamir. They introduced this attack in 2001. They observed that the first bytes of the key stream are not random. With certain IVs, an attacker knowing the first byte of the key stream and the first n bytes of the key can derive the following byte of the key, n plus first. So this means that if you know the first byte, then you can capture the second byte of the key, and so on and so forth. So, but this only works with certain IVs. So some IVs in this attack were considered as weak IVs, and this attack worked on that. And you might think that, okay, the attack only works when you know the first byte of the key stream and the first n bytes of the key. But you know, the first byte of the plain text in WEP comes from snap header, which is almost always AA in hexadecimal notation. So from the ciphertext, if you XOR this value, which is the plain text, you capture the key stream byte, and this way you perform the attack. So most of the time the attack works. But this attack was also, there was a better attack by Tews, Weinman, and Pishkin, and they provided this attack in the paper titled "Breaking 104-bit web in less than 60 seconds." And in this attack, the authors does not need weak IVs. So the attack works for all IVs. So these attacks are actually implemented in many software tools. One of the favorites, I think, is Aircrack NG. So if you have Aircrack NG and there's a web, a Wi-Fi router that's actually running web, then you can just use this software and capture the web key, and you know, provide and obtain an unauthorized access to the wireless LAN. So it is very easy to crack this web password. So actually you can capture any web key. So for this reason, WPA was quickly developed as a remedy to this problem and became available in 2003. So now that we know the WEP is not secure, and it is replaced in 2003, you might think that no one is still using WEP, but our routers allows us to choose which security protocol you want to use. So almost all of them allows you to choose something between WEP, WPA, and WPA2. And people who doesn't know which one is secure sometimes uses WEP. And some people, for some reason, think that it will provide faster internet connection, but WEP is not secure. So if you ever discover a Wi-Fi in an area which actually uses WEP, you can just check by using your mobile phone which encryption they are using. So if they're using WEP, it is your responsibility to warn them that their Wi-Fi communication can be cracked in a minute. So let's talk about WPA, Wi-Fi Protected Access. It is shortened as WPA. WPA was developed by the Wi-Fi Alliance in response to the discovery that WEP was insecure. So it became available in 2003. This is also referred to as draft IEEE 802.11i standard. It uses AES encryption instead of RC4. So we talk about this also during the TLS. We stopped using RC4 once we discovered that it is no longer secure, and everybody moved on to AES. So nowadays, if you have a router at home, most probably you're using AES instead of RC4. So it also has many other security improvements over WEP, so it doesn't simply the replacement of the encryption algorithm. But it is not a mature standard. It was prepared very quickly in response to WEP being compromised. So for this reason, people updated it to WPA2. So WPA was revised and integrated into, again, our standard with I in 2014. The amendments obsoleted the broken WEP protocol. It implements authentication services described in IEEE 802.1x. The final form of this standard is referred to as Robust Security Network, RSN. So for the rest of the talk, I will just simply say RSN for this standard. So how the authentication work in RSN services? A protocol is used to define an exchange between a user and an authentication server, AES, that provides mutual authentication and generates temporary keys to be used between the client and the access point over the wireless link. So access control works as follows. It enforces the use of authentication function, routes the messages properly, and facilitates key exchange. It can work with different authentication protocols. And privacy with message integrity is as follows. MAC level data, for example, an LLC PDU, are encrypted along with the message integrity code to protect against modification. And RSN has the following elements. The services and protocols are defined like this. For access control, you have to go to the standard with port-based access control. Authentication and key generation is provided by the protocol Extensible Authentication Protocol, EAP. And for confidentiality, data origin authentication, and integrity and replay protection, we have TKIP and CCMP protocols. So now let's look at the cryptographic algorithms that we use for these protections. So for confidentiality, in the standard port-based access control, we have the following cryptographic algorithms. TKIP uses RC4, CCM uses AES in the counter mode, and we also have NIST keywrap. So if you roll back your security and move back to WEP, you can use RC4 with TKIP, but almost default value for almost everybody is AES and CCM. For the integrity and data origin authentication, we have HMAC SHA-1, HMAC MD5, TKIP uses Michael MIC, and CCM uses AES CBC MAC. So remember, we already talked about block ciphers, mode of operations, hash functions, and message authentication codes. So all of those algorithms we talk about there actually appears here also. And for the key generation, we have HMAC SHA-1 or RFC 1750. So these are the algorithms that are included in RSN. So now let's talk about 802.1x. So this is an IEEE standard for port-based network access control, which is shortened as PNAC. It is part of the group of networking protocols. It provides an authentication mechanism for both LANs and VLANs. It supports the use of the Extensible Authentication Protocol, EAP. So let's talk about EAP. It is made up of 3 entries: supplicant, which is the client device that wants to attach to a network; authenticator, the network device, for example, access point, responsible for authenticating the client; and the authentication server AS, the authority implementing the policy on granting authorization requests. So sometimes the access point can act as the authentication server or communicate with some external authentication server, for example, Redis server using LDAP database. So actually this is what happens in our university, and almost every university or big companies and so on use this approach. So instead of using access point for authentication, you have an authentication server, and most probably you are providing MAC addresses of your devices to this authentication server. So the authentication is performed through this operation. There are various types of EAP. So EAP TLS, EAP TTLS, and EAP LEAP, and so on. But if I'm not mistaken, in our university we are using EAP TTLS. Also, when if you're using mail servers, you also have to provide encryption through that protocol.